All right, so we have a second talk given by Jara from Aalto University, and he's going to talk about local problems in sparse files.
Yeah. Did you also steal the USB thing? It's here. All right, so I'm also going to talk about basically similar problems that Yannick introduced already, but the model of computation is going to be a bit different. And just to give a short overview of the talk, I will first do this kind of mandatory introduction to the models of computation, even though you heard about them previously. But perhaps most interestingly, I'm going to talk about how to take algorithms from the local model that Yannick introduced to this MPC world. And then I'll try to convince you, or at least explain where we are stuck at the moment, and then give some ideas on how we might be able to get forward. All right, so this MPC model, it's the same as you heard about before. So we have some graph as an input, and as these kind of important parameters, we have n nodes and m edges. You first partition this graph into some bunch of machines, and then when you partitioned it, the machines can talk to each other in all-to-all fashion in synchronous rounds. And then the parameters to keep in mind is that we have some m machines, and all of them have this S memory per machine. And here the kind of key thing to keep in mind is that the machines can never hold more than S words of memory, which then kind of means that this is the bound of how much they can communicate. And just for terminology, I'll call this m times s the total space, which is kind of how much is available in the whole system. And clearly this must be at least the input size. And we often kind of split this model into regimes, but now in this talk you only need to care about this low space thing, where the memory is sublinear in the number of nodes. And this kind of means that we cannot use, for example, sketches of the whole graph or anything. So no one can store a thing like that. And Yannick already talked about this local model of message passing. And perhaps the good thing to keep in mind here is that each node corresponds to a machine, and they're only allowed to talk across the edges. So you cannot talk to everyone. You're restricted on the edges of the graph. And actually now, for this MPC model, it's maybe convenient to think that each node is a machine. I mean, that doesn't really match with the things I said previously, but just imagine that each node is a virtual machine. So you're still restricted by all the things I said, but just think of all of them as machines, and it will make things a bit easier. All right. And then you can kind of see this local model of distributed computing as in T rounds, collecting a T-hop neighborhood, and then that maps the node into its output. So for example, like whatever you choose in this LLL, or whether you're in the MIS or not, or what is your color. And why is this convenient? Well, in this MPC model, we have this technique called graph exponentiation that allows you to collect these neighborhoods fast. So if you look here, like in MPC, we can collect them in log of T rounds. So basically, you're potentially getting an exponential improvement on the runtime. And after you collected this local neighborhood, then you can just simulate whatever the local model would do. All right, so let me quickly introduce this technique. So if we just think of a line, it's kind of easy to see that if in local you want to talk from left to right, the message will have to travel like proportional to the length of the path rounds, and there's no way around that. But in MPC, if you now think of all of these nodes as machines, this, for example, this U3 guy, it can just tell its neighbors that, look, you're within 2 hops. And now you can think of this dashed line as a virtual edge. And if you do that on everyone in parallel, then you create G squared. And now in MPC, because you don't restrict to this, the communication to the edges, now you can use actually this G squared to communicate. Okay, then you can repeat and get G to the 4. And if you repeat this I times, you now created G to the I. And now you can either think that, okay, now I can communicate on this graph, or I actually already collected all the information I wanted. But there's a catch, because I mentioned that the local space is this S thing, and if S is n to the something smaller than 1, you need to ensure that the local neighborhood isn't larger than that. So as long as the local neighborhoods are small, this works out of the box. Does it make sense? Good. And now, this coloring problem that was mentioned a few times in the previous talk, I guess here's a nice example of kind of how to improve from the local model. So we know how to solve delta plus 1 coloring in polylog log n rounds in the local, and in MPC we can do triple log. And now don't be fooled, it's not just that I take the local algorithm and I shove it in this framework. So there's a lot of kind of these sparsification tricks to make it work, but the runtime eventually comes from this fact that you will shove some parts of the algorithm into this exponentiation framework. And I also want to mention that you can sometimes do even better. Actually, we kind of thought for some time that maybe there's some sort of a relation that all these local problems get stuck eventually in this exponential increase, but it's not true. So there are, like, if you want to approximate independent set sizes, even pretty badly, in local you need log star n rounds, and in MPC you can do it in constant rounds. And I mean, clearly here's a better improvement than exponential. All right. So then just to quickly recap what I said so far, like if we now suppose that we have some, yes. Great question. So I guess with public randomness, still not. Exactly. Okay. So I didn't say nonsense. But we actually found an LCL problem, like bounded degree graphs, where public randomness helps.
All right, because I just want to check, is it the only gap is that in MVC you can share your randomness and in local you cannot? But you're saying n over delta you cannot do in local even with public randomness. If I sound perfect, 1 over delta. Okay, anyway, so I think you are saying exactly the right thing. If I now got it right, so here, where this thing comes from is that you de-randomize, basically, like you say that let's pick consistently the same answer. So you kind of can run some algorithm in parallel log n times and then just take the best output. And this is great for approximation, because you can kind of just take the best answer. That doesn't really work in constraint satisfaction. And I'm soon going to say something about exactly that. All right, so local algorithm with runtime of t, there is this graph exponentiation technique where you can potentially improve exponentially, but not better. So basically as soon as you shove things into this exponentiation framework, then you won't be able to do better than that. And it's kind of a nice question of whether these local constraint satisfaction problems somehow strictly belong into this class.
like, would there be a way to solve MIS or maximal matching faster? We don't know, and I don't even know what to guess. But then, as Sepper said, there are then problems where we can do better than exponentially faster, but so far we only know approximation type of problems. And as Sepper pointed out, there you can kind of cheat. Because in local, if you randomly try to, like, let's say, find a large independent set, and there's nodes far away, you cannot agree with them, like, what kind of solution to take. But in MPC, you can run things log n times in parallel and take the best answer. So you can kind of turn expectation into high probability, and then things become very different. All right, and then just to pitch an open problem for MIS, what we know currently is that in local, we have some algorithm that works in log of delta time. Would actually be nice to introduce this, but in half an hour not. And in MPC, we kind of use this exponentiation framework to speed it up. We cannot do log delta, but I mean, we still use these ideas. And I mean, the question is, could we get closer to this locality barrier? In principle, we could get even below it, but I think it's maybe better to try to close this gap first. Good. So any questions so far? No. All right, so next I'll go in a bit more detail into this MIS algorithm that I just mentioned in the previous slide. And then I'll try to pinpoint the place where we are stuck. So as said, it would be nice to introduce this local algorithm, but it's not really super tedious, but the analysis is, and without that, it doesn't make so much sense to bring it up. So now just believe me that there is a nice local algorithm that works in log of delta rounds. And what we do in MPC is that we show that the local algorithm, like, you can think of taking a snapshot of what currently is happening in the algorithm. And then for root of log delta rounds, we can ignore all high degree nodes. I will soon say what is high degree, but just think of it like we know the state of the algorithm, and then somehow we show that we can ignore high degree nodes. And I mean, in this case, we call that step the sparsification step. So we somehow randomly make the graph sparse for some time and then simulate root log delta rounds fast. And essentially, I'm squeezing like this many rounds into single MPC rounds. And now if you kind of just put the numbers together, you can see that if I repeat this compressed root log delta rounds, root of log delta times, then I will get into log delta local rounds. So that's just the basic idea on how to speed this up. And here, now, what is high and what is low degree? So I mentioned earlier that to make this graph exponentiation work, we need to ensure that the neighborhoods fit into memory. And if you now kind of say that low degree is something below 2 to the root log n, and collect the root log delta, and now collect the root log delta neighborhood, then I need to guarantee that this is smaller than, I mean, here I wrote smaller than delta, which is smaller than S, and just now take it for granted that you can make delta smaller than the local space. And okay, so I already basically said where the round complexity comes from. There's this log delta that comes from the exponentiation part. So again, here that means that there's basically no hope of getting better than that. But this also feels somehow like a fundamental barrier for this approach. So if I want to split into high and low degree nodes, Well, it seems like I cannot do much better. And I mean, our analysis is tight in the sense that at least with what we tried, you cannot make it better than that. But on top of that, when we do this like compressing of the rounds, we really shove it eyes closed into this exponentiation framework. And that also means that there's no hope with this approach to getting below log of delta. Now, to mention something that Yannick talked about without saying anything about details, in the algorithm I mentioned, eventually the graph will do this shattering business that Yannick said, that it will turn into small components. And how you solve that in MPC? Well, the components are small, so we'll just gather basically the whole thing onto a single machine. And again, I'm closing my eyes and I don't care at all what happens there. I'm just going to collect everything. Now you might wonder why I was so hand-wavy and in both cases said that we do black box exponentiation. Well, I'll try to now explain where this came from. So, well, first of all, many of the problems in this like local constraint satisfaction, they do the same thing. Like eventually, I will just take local algorithm, close my eyes, and shove into this exponentiation framework. And I would somehow like to forbid that, because as soon as I close my eyes, there's no way to getting around this locality barrier. And one property in common with all these algorithms is that since you collect this t-hop neighborhood eventually, you will also increase the total space that you need in the system. So there's kind of no way of saying that every node just collects a constant amount of words, because I'm like literally collecting everything around me. And what I've been trying to do recently is to just change the game a bit by saying that you're not allowed to use more than exactly linear amount of total space. And just to turn that back into what I said before, that essentially forbids me from closing my eyes. I'm never allowed to just blindly exponentiate and collect everything.
Small component, why do I have to send each of its vertices to a separate machine? If I send the whole thing to a single machine, then I'm not using too much memory. I have like X vertices. Is it because those X vertices may have X square edges that that machine become dense?
Well, there are somehow many reasons for that, but one of them is that when you do these small components, you still might have some dependency on delta. And I mean, I've completely ignored that, but that might influence the round complexity. But then if you simulate local, then you can forget about that. Now I'm really being hand-wavy, but sometimes you have dependence. Okay, I thought you wanted to say something.
Yeah, once you're done.
And another problem is that when you're collecting the component, everyone needs to exponentiate. You cannot just have one guy waiting for the messages to arrive, but you're first kind of collecting all of your neighborhood, like doing this exponentiation business I explained before, and you need that to get the data to one node fast. And I actually later hope to show a small, easy trick on how you can sometimes avoid that. All right. And one thing we might be able to get this linear total space thing is to do something smarter on this sparsified graph I mentioned in the context of MIS. And like there now, very informally speaking, the boundary we had in our sparsification was that we get the max degree only up to some point. But if we were able to do something smarter in the sparsified graph, maybe we could leave the max degree higher and then compress more rounds at once. I don't know, but it might help to think of algorithms like that. And I mean, here I basically now already wrote that I said before that if we do linear total space, at least we need to think a bit differently. So we should come up with some new algorithmic ideas. And I guess that we at least should learn like different ways to locally collect data fast with that, like not just closing eyes, but doing something a bit smarter. Right. And then as the last thing, I want to address Sepper's question a bit and show at least one nice new trick that we learned when we thought about this linear total space. And now I quickly need to explain what are locally checkable labeling problems. So we mentioned these MIS and maximal matching and LLL problems where you kind of can locally check whether your solution is correct. So if you think about MIS, I can check whether I'm in the MIS or at least one of my neighbors in the MIS is in the MIS and conflicts. And the locally checkable labeling problems, they have this extra restraint that it's only on constant degree graphs. And now you might think, aren't all of those trivial? Well, it turns out not. So many of them still remain hard, even if you're on bounded degree graphs. There's a very nice result from previous work by Cheng, Kopelovitz, and Petty, who showed that if you can solve an LCL faster than log n in the local model, then you also have a log star n round algorithm in the local model. I'm not going to go into that. I just want to use some of their tricks to do something similar in MPC. And here, again, one of the nice things is that the only ingredient they basically need is a distance k coloring. If you don't know what that is, just think of it as coloring the kth power of g. And in the local model, since we have k a constant, there's this kind of well-known algorithm by Lineal who solves this thing in log star n rounds. And the only thing here you need to keep in mind is basically that if you have a C coloring, you can turn it in one round or maybe two to a log of C coloring. So you can kind of reduce the color space exponentially. Don't care about the delta squared there too much. I just left it there so that I'm not lying too much. Great. So actually, we can even simplify this problem further because delta and k are constants in this case. We can reduce the whole problem into three coloring pseudoforests. And you can even assume that they are rooted, even though a pseudoforest doesn't really have a well-defined root, but just think of a rooted tree. And the algorithm by Lineal also says that it's enough to look at log star n of your ancestors to solve this problem. But now, okay, now you might think that, well, isn't this kind of done? Now we get a log star n MPC algorithm. What more would I want? Well, first of all, faster. And second of all, I would really like to focus on like MPC issues here, really make sure that we are doing smart things in MPC and not just collecting local neighborhoods. So like the tempting approach would be just the leftmost node. It kind of does this exponentiation business, collects the log star n neighborhood and simulates the local algorithm. But well, what happens is that you now need n times log star of n words of total space. So not allowed. And I actually think this might have been suggested by Yannick, this algorithm earlier, that one nice trick you could do is that you use this algorithm by Lineal I mentioned earlier. So typically we assume that all the nodes in the graph, they have some unique identifier just so that you can tell them apart. And then these unique identifiers, they basically correspond to a coloring where all the colors are of length log n bits. And if you now do one round of Lineal, you get into log n bit coloring. Now, if you think about gathering the like log star and neighborhood of ancestors, what is the size of the vector that corresponds to these colors? Well, it's log n times log star in bits, which is clearly smaller than log n. So are we done now? It seems like that, but then we realize that there's still trouble. Because if I'm that guy and I want to talk to all of these machines, I need to somehow store the addresses of these machines. So I need to know which machine holds which of these nodes. We have potentially like some poly n machines. So they also need identifiers of length roughly log n. So not in the goal yet, but we can do another nice trick, which is just storing one address. Now, if you think about what happened in this exponentiation, is that like first, if I'm that guy, I know the color of my ancestor, and I know that guy's address. And then I can do one round of exponentiation, and then this guy has all the information I need. So I only need to remember what is his address. And then I can continue this exponentiation. I store one machine address and then the vector of colors I need. And then I actually get to linear in n words of space. Now, just to mention the result we had, basically it's now kind of this MPC version of this result by Chan, Kopelovich, and Petty, which says that if I have a fast local algorithm, I get a log of log star and round MPC algorithm. I get it optimal in terms of memory, because as I said, you need linear in n words of space, because that I need to store the input. And like subjectively speaking, nice property is that I need to do something smarter than this kind of naive thing. I mean, you can have different opinions on that, but anyway. And then there are some reasons why one could have hoped that this runtime is also optimal. Maybe Arthur disagrees, I don't know. But at least it's kind of a local constraint satisfaction problem. And there are some results that say that some classes of algorithms cannot do better. And we don't know if that can be extended to all algorithms or not. I don't know what to believe, but at least conceivably it's optimal even in terms of runtime. I think I'm now out of time. I wanted to make some chicken egg speculations, but maybe I don't do it now to be on time. 2 minutes, okay. My timer here says different. Okay. No, but I had this timer when I started, but never mind. So one thing I wanted to mention is that now I said that it would be great to do smart exponentiation, but it's not so clear whether smart exponentiation is just another way of phrasing brilliant graph sparsification. I don't know, but at least it's not so clear whether I can always just be better at sparsification and then do this eyes closed exponentiation. But that I don't know. And well, that brings us to this chicken and egg picture. All right, so now it says 29 minutes and 20 seconds. So I'll stop here.
We have time for questions?
Yes. Can you say a few words about this sparsification for your MAS algorithm for the large degree? How do you get the degree down? Or like what do you do with large degree?
All right, so the idea is that Mawson's algorithm, what it basically does is that first everyone starts with, like they fix a probability of 1/2. And what you do with this probability is that you beep with that probability. And if I beep alone, then great, I can join the MIS because the beeping kind of says that I'm a candidate to join the MIS. And if you hear another beep, then you lower your probability. And now, like these probabilities, they live a lot. And now you can, in local, you can calculate like what is the expected number of beeps I hear in my neighborhood. And if it's high, then I can say that, okay, I shouldn't do anything because the next few rounds anyway, I won't be joining the MIS. There's basically no way. So I'm kind of putting myself on hold, and there the best threshold was this root of log delta rounds that I can be on hold. Then I need to update my probability and continue. And then this basically results in the fact that either no one is beeping in my neighborhood, and if many of them are, then I'm putting myself on hold. And I mean, if many of them are, then I'm kind of high degree, and if not many of them are, then I'm low degree. Like many of my neighbors are also not doing stuff. I mean, intuitively like that, there's technicalities, but that's how you get rid of high degree nodes.
And this also works in a regular part where everyone has high degree, because you don't want everyone to be on hold.
It's fine to have them on hold because everyone will then drop their degree while they're on hold. So basically you're kind of just adjusting the probabilities faster to lower. And then when you continue, then you maybe increase them for a bit, but it's fine if everyone goes on hold.
Are there any problems for the large delta where this exponentiation is giving optimal bounds? In your case, MIS, for example, you have root of log n. So are there problems that you really are reaching the exponentiation bound, so log of local?
Log of local. Large delta. Well, I mean, you have this coloring algorithm, and if you just split the palette, you kind of reduce the whole thing to small delta. I mean, I guess at least coloring, you can, like, in a sense, get from large delta to small one. And also with this Mossen's algorithm, like we didn't think about it much, but if you have large delta, then kind of you have a better probability of stopping the process fast.
Okay, my question is maybe for general graphs rather than ignore delta. So you don't have any information about delta.
Yeah, no, I understood it, but like I said in this algorithm we had with Mossen, like if you have high degree, like locally, I'm high degree node, then I kind of get out of the game faster. So in a sense, you will get to low degree graph fast. But like besides coloring, I don't have an example on top of my head where things turn into low degree fast.
Isn't connectivity another example? You can do it locally, or you were looking for LCL.
Okay, true. The connectivity is a good example. Because in connectivity, the higher the degree, the better, because you contract nodes depending on how many neighbors you have in some hops. Yeah, you're right. I also try to think of LCLs, but connectivity is a good example. Yes.
Yeah, so when you're doing exponentiation and shattering, you're putting different parts of the graphs in a different machine or a different large enough neighborhood. How do you take the answers from different machines and stitch them together into a cohesive answer? Like what are the common strategies you use for
Yes. So that's a good question, and that's why I said at some point that think of them as virtual machines. So sorting is fast.
Okay.
In MPC, so you can basically, however the input is distributed, you can quickly turn it, like in constant rounds, turn it in a way that you have the nodes on individual machines. Of course, if the degrees are very high, then you need to do magic, but like on a high level, just think that you can in one round have the nodes on individual virtual machines, and then all of this becomes a bit less annoying. Right.
Last question.
Yes. What's your conjecture about this locality barrier and its importance for LCL problems? Can one go below for these LCLs or not?
Well, let's say that I was optimistic at some point that you cannot, and every time I've been wrong. So I guess now I will believe for a bit that you can go below, and I hope I'm wrong again.
All right, let's thank Jara again. So we have we have